Okay, our last scenario here is dealing with the ability to taste a chemical called PTC. The problem states that the ability to taste PTC, which some people can, some people cannot, is due to a single dominant allele. You've sampled 200 individuals in biology and determined that 182 could detect the bitter taste of PTC. So 182 people are either homozygous dominant or heterozygous. Because we can't split up those two groups, we don't know out of those 182 belong to homozygous dominant and how many belong to heterozygous, we really need to start off by thinking about our non-tasters. So in this scenario, 18 out of our 200 individuals are non-tasters. In other words, 18 individuals are going to be homozygous recessive. Homozygous recessive in our Hardy-Weinberg variables is represented by Q squared. So Q squared in this scenario is going to be 18 over our total 200. Well, if I reduce that, that's 9 over 100, or 9%. I need to write that as a decimal. Q squared is going to be 0.09. Okay, once again, why did I find Q squared first rather than thinking about the dominant people? Out of this 182, I don't know how many of those are homozygous dominant or heterozygous, but I do know for sure that anyone who's a non-taster, which is 18, anyone who's a non-taster, I know for sure they're homozygous recessive. Okay, back to this, Q squared is 0.09. So if I square root both sides, be careful with your decimals. Q is going to equal 0.3. 0.3 times 0.3 is 0.09. So 30% of my alleles are going to be recessive or little t's. Therefore, 70% of my alleles must be big T's. So Q is 0.3, P is 0.7. Remember, those add up to 1, or 100% of my alleles. Okay, genotype frequencies. Homozygous dominant. Hopefully you get by now that that's represented by P squared. P in this case is 0.7. Square that, 0.49. In other words, 49% of my population is homozygous dominant. Those would fall into the tasters category. Homozygous recessive. When I started this problem, I determined that 18 out of my 200 were non-tasters, or in other words, I determined that 9% of my population were homozygous recessive. My last category here is heterozygous. Once again, there's two different ways I can calculate this last category. I can either think about the fact that these three categories together must add up to 1. So I could add up my first two groups, subtract that from 1 to get my final group. Or I can actually do the math where I take 2 times P times Q to figure out my last category. I always do P times Q. 7 times 3 is 21. So 0.7 times 0.3 is 0.21. I'm going to double that because I need to multiply it by 2. So the full term, 2PQ, is going to equal 0.42. Or in other words, 42% of my population is heterozygous. I can check my math because these three categories should add up to 1. So my allele frequencies add up to 1, and my genotype frequencies add up to 1. The last note here at the bottom is really important. Okay, make sure that you understand from your lab and from your notes the 5 mechanisms that can cause evolution, or the 5 conditions that can be met for equilibrium to occur. Remember, the 5 mechanisms that cause evolution will be the complete opposite as the 5 conditions that must be met for no evolution, no change, or for a stable population to remain in equilibrium.